Wookie jokey. So we made our way, I think, through an entire chapter in one day, pretty much. Chapter 7 is kind of short, at least for the stuff that I'd like you guys to focus on. And that doesn't mean it's any less important. In fact, I would say it's probably one of the more important chapters, especially for those of you who are going on through organic and biochem and all that kind of stuff. You'll see those ideas coming out again and again and again as we go through and describe the different reactions and properties and all the different kind of, let's say, information that we expect from these upper division kind of chemistry courses as you guys move forward there. So definitely an important chapter, but granted, a little bit shorter than especially something like chapters 4 and 5 there, right? Those took quite a while to kind of slog our way through, but we made it, right? So we're going to move on into chapters 8, but I kind of took chapters 8 and 9 and parts of 11 and just kind of smushed it all together just because that's kind of the way that I see it logically flowing. So 8 and 9, you'll see us hopping back and forth quite a bit between different parts of it. So for those of you guys following along with the book there, don't be too surprised if I suddenly bounce in between things. But all the information I will cover will come from those 2 chapters. And the things that will come out of chapter 11, I'll point that out to you guys when we get there, right? We're not going to be doing all of chapter 11 because we don't need to, okay? Right? So I know you guys are terribly interested in the behind the scenes work, but what I mean is, let's close this real quick. So fortunately or unfortunately, whichever way you want to think about it, it's not like I come in and pick exactly the topics that I want to talk to you guys about, otherwise this class would look a lot different. But there's a governing body called the American Chemical Society. They kind of dictate what should and shouldn't be taught in general chemistry, and that kind of plays into the MCATs and all this other kind of stuff too, right? So it's not just me making decisions. I'm a mere vessel, so to speak, to deliver knowledge, not necessarily pick the topic. So that's why we kind of pick and do the things that we do, for better or for worse, and that's why we kind of skip through some things also, just because if the ACS doesn't really require it, and the MCAT's not on the MCATs, and you guys aren't chemistry majors, so we probably won't need to see that again, right? But anyway.
Chemistry major?
Huh?
Chemistry?
You're a biochemistry major, right?
Kind of same family.
Chemistry is the far superior major, is all I'm going to say.
One has to do with chemistry.
Anyway, but let's get started with prayer then, and then we'll keep making our way through the rest of this here. But Lord, we just thank you yet again that we get a chance just to come before you, Lord. And Lord, we just thank you that you've given us the blessing of being able to just talk with you whenever we want to, Lord, and more importantly, whenever we need to. Lord, just help us to understand, what it is to have a relationship with you, and just help us to grow that relationship today, Lord. Just ignite that fire in our hearts again, Lord, just to seek after you in all the things that we do, and all the things that we pursue, and in all the actions that we take, Lord. We know that you put us here for a purpose, Lord, and we just pray that you open our eyes to see that path that you set before us, Lord, and to speak clearly to us all, and just guide us on that path, Lord, and let us follow in your footsteps. We just pray all this in your name. Amen. All right. So, my favorite chapters, 7, 8, and 9. This is all of chapter 7. I could have just basically given you guys a slide and say, I would have used the M word, which I don't really like to use, which is memorize, right? Rather, I want you guys to understand this, okay?
So what you're saying is francium is really metallic, and
What?
helium is really non-metallic.
What I'm saying is there is a set of periodic trends that are extremely important to recognize, right? And that the trends are the ones that we talked about. We talked about radius first and how radius governs, or how we can use the idea of atomic radius to understand all the other principles that we need off of the periodic table. The idea of ionization energy and electron affinity and all that kind of stuff, okay? It all has to deal with how close or how far that electron is from the nucleus. The closer the electron is to the nucleus, okay? The closer the electron is to the nucleus, the harder it is to remove that electron. The further away from the nucleus it is, the easier it is to remove that electron, right? That affects ionization energy and electron affinity, okay? Kind of in both in the different directions here, okay? That's what it is. So I expect you guys to know this, and you guys will probably on the next exam or whatever, you know, draw your arrows on there, but I expect you guys to be able to explain this to me, okay? Explain why we see the periodic trends in the way that we do, okay? That's what's going to be important. All right, so from there, okay, we go into our chapter 8, 9, 11 kind of hybrid there. Now, what we're going to be doing in this chapter is, now that we understand everything there is about the periodic table, 100%, right? Now, all we've been really kind of doing is describing the property of an atom, okay? We constructed a hydrogen atom, and we modeled that atom mathematically with the Bohr equation there, right? And so now what we're going to do is take two atoms and put them together to form a bond. And then we're going to take 20 million atoms and put them together to form a giant big molecule, or whatever you might want to say with it, right? So what we're going to do is take individual atoms, put them together to make something bigger. So we're going to learn to describe the geometric shape of every molecule in the entire universe, okay? So we're going to do that all in one chapter. It's going to be pretty impressive, okay? We're going to describe bonds, okay? Whether we have different types of bonds, ionic and covalent and polar and nonpolar, all this kind of stuff. We're going to talk about the strength of those bonds qualitatively. We've already talked about the quantitative strength of bonds, right? That's our enthalpy discussion there, right? How strong or how weak bonds are relates to how much energy is gained or released as you break or make them, right? That's what we kind of talked about there in chapter 5, okay? And so now we're going to be able to visualize how these molecules are put together, okay? So that's kind of going to be the main kind of path that we take through chapters 8 and 9 here. Okie dokie. So as usual, or as I try to do, I try and stick these very important visual slides in here for you guys, right? Because otherwise, why make a PowerPoint if it's just all words, right? It's a visual medium, right? So anyway, when an atom exists, right, it has atomic orbitals. That's what you guys have been talking about, right? Or what we've been talking about, the S, the P, the D, and the F orbitals, okay? We are going to use those orbitals to make our bonds, okay? Now, you guys already knew that, okay? You might have not been able to verbalize it in such a way, you know, but what lives in our atomic orbitals? What lives in any orbital? Electrons. What does chemistry? Electrons, right? So it should make sense, right, that whatever electrons are living in those atomic orbitals, specifically are valence electrons, okay? They're the ones that are going to be coming together to make bonds, break bonds, transfer electrons, all this kind of stuff. Core electrons aren't really going to do anything for us, okay? Now, we can explain why that is because of the stuff that we learned about in chapter 7 there with ionization energy, right? It costs too much energy to move those core electrons around. Not going to do anything with that, right? So what we're going to do is take our valence electrons and use those to make or break bonds, okay? And those live, or those start their life in atomic orbitals, I should say, okay? When atoms form bonds, atomic orbitals turn to molecular orbitals, okay? Now, that doesn't really have any shocking consequences to it at the moment, okay? We take individual atoms and bond them together and we form molecules. Atomic orbitals become molecular orbitals, okay? Now we're going to learn about something called MO theory, or molecular orbital theory, and that's going to describe how we can construct our more complex orbitals based off of our atomic orbitals. We're going to explain why oxygen doesn't kill us all in a violent fury of erupted combustion here, okay? It's actually a pretty important idea, right? So it's an interesting idea too, okay? So we'll talk about how MO theory kind of affects a lot of things behind the scenes, okay? And then the last point there is just what are orbitals, and that's kind of what we discussed about. The pictures that I have here are not arbitrary. They're showing the formation of molecular orbitals, okay? And we have to think here for just a second to keep something in mind. right? So if we have a p orbital, it doesn't matter what it is, the px, the py, the pz, who cares, right? Remember, the shape of the orbital represents a mathematical probability about where we find an electron, okay? I give you guys an equation, you plug it into your calculator, you get a shape out of it, right? That's what our orbitals are, okay? So if I mix two orbitals together, this is math, what do I get out of it? Math. You guys get what I'm saying with this? You mix one equation with another equation, you generate a new equation that has characteristics of the two things that you put in there, okay? That's all we're saying. I'm just adding things together. That's all. It looks complex, I'm not gonna argue that. It's pretty complex to explain, won't argue against that either. The math is complex, but you guys see any equations?
Mhm.
I don't, right? I just see visualizations of this stuff, okay? That's all it is. And so when we get to, hang on just a second. So when we get to this idea of MO theory, I'm gonna explain it to you guys as simply as I can. But this is what I want you guys to remember. All we're doing is mixing mathematical equations together to make a new equation. And then we just draw it as a representation of whatever we mix together, okay? Garbage in, garbage out is what we're going to be doing with that, right? What's up?
Why is the coefficient pi?
Because when you mix two p orbitals together in a specific arrangement, you make what we call a pi orbital, a pi bond.
Does pi in this case have its typical mathematical value of 3.14?
No.
Okay, so it's just a simple.
It's just a consequence, yeah.
Okay,
Yep.
thank you.
Yeah, I don't know why, I don't know to be fair, I don't know the historical answer for why we call those pi bonds. I'm sure there's some reason, right? You know, most of these things aren't arbitrary, it's just, there we go. That's what we call them so far, right? All right, cool. So let's talk about the different types of bonds that we have here. There's really three bonds that we kind of care about, and really we could condense those down to two of them. Ionic bonds is what we've been talking about so far, okay? So if I ask you guys what an ionic compound, or let me back up that statement for a second. Ionic compounds are what we've been mostly talking about so far, right? We spent a lot of time dealing with the solubility of ionic compounds and figuring out the charges and all this kind of stuff that everyone remembers 100%.
Yeah.
Right? Okay. So you guys do know a lot about ionic compounds at this point, okay? So it shouldn't be a big shocker that I say that ionic compounds, okay, have ionic bonds. I know, it's amazing. But you guys already kind of understood this also, right? Because what is an ionic compound? Well, we'd say it's, you know, the definition we kind of began with, it's between a metal and a non-metal, right? The broader definition is what?
A positive, or an ion, an
Cation,
anionic.
Right? Something with a positive charge and something with a negative charge. Cations and anions. What happens when you put things with negative charges close to each other? They'll stick together, right? So you guys already understood this, right? That's all it comes down to. Something negative is going to attract something positive, and they're going to form some kind of cohesion between them, right? And we'll call that our ionic bond, okay? Now, ionic bonds are different than the other types of bonds that we're going to learn with. If we want to drastically simplify this, okay, ionic bonds are non-directional. That means that they're just, you can think of them as giant blobs of charge. And if you have a negative charge, they're just going to attract whatever positive charge is around them, okay? Covalent bonds are directional and are localized in one, how do I want to say this, axis, one direction, one point, okay? And think of them as vectors, right? They have magnitude and direction. Much like what we learned from Despicable Me, right? Remember the guy in there, right? He says his name is Vector. And thank you, one person. Everyone else, no, Dr. H, I don't watch that kind of stuff, right? But anyway, okay? So ionic bonds really don't have a, let's say, directionality to them, although I am simplifying that quite a bit, okay? So what I mean by that is this. We're going to learn a lot about bonds, we're gonna be able to draw them, we're gonna be able to put them together and all this kind of stuff, blah, 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 right? The stuff that we're gonna learn applies predominantly to our covalent bonds, okay? Ionic bonds are a little bit different. We could talk about crystal lattices and packing and all these kind of things, and that's where we kind of spend a little bit more time with our ionic compounds. But for the most part, we're going to be dealing with covalent in here. Does that mean, and this is important, does that mean that our ionic bonds are unimportant? Well, no, of course not, because we just spent a bunch of chapters learning all about them, right? So what we're going to be doing, though, is talk a little bit more about covalent and ionic. You got a question?
Yeah, for ionic and covalent bonds, do the electrons, so like, there's a difference in how the electrons are like transferred? There's a sharing?
There's a
of
difference in
electrons?
where the electrons live,
Okay.
right?
Do they move throughout each other for both of them?
What do you mean?
So like, ionic bond, is it a transfer of electrons?
Yes.
Versus a sharing of electrons?
Correct,
Do
yep.
they move about the
Yep.
orbitals for ionic and covalent?
No, for covalent. Ionic, right, if you think about them as the transfer right there, it's if I completely gave you, I don't know, my laptop, right, you know, as opposed to if we shared one laptop, like something stupid, right, you got, I couldn't think of a good example there, but right, but you get the idea here, right, you know, it's if somebody completely owns something, right, versus whether that's shared between two people, right, that's the idea there. All right, so don't forget the definitions of covalent and ionic. That's going to be important because if I'm going to ask you guys to draw covalent bonds exist in covalent molecules, right? Do you guys remember the naming rules for your covalent compounds?
Yeah.
Right? Your di and your tri and your tetras, right? Remember your covalent compounds is where your prefixes were, right? They are all our invariant species, right? Carbon dioxide, right? Phosphorus tetrachloride, right? Things like that, right? So anyway, metallic bonds, used to be one of these kind of historically discussed topics. We don't really deal much with it anyway. Metals kind of exist in what we would typically describe as a sea of electrons, where all the atoms just kind of share everything, and it's a giant blob, and blah, 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 and you go through that. It's there, it's important, it's extremely important, especially, we don't have engineering here, but if you guys went on to any kind of engineering, that'd be important, and you guys would spend a lot of time talking about it there, but that's fine. Anyway, so at the end of the day, what we're going to do to describe our covalent bonds, and mostly any type of bond, is talk about Lewis theory there, right? And again, just to put the point on paper here, right, it's going to be our valence electrons that do the thing, okay? So when we are making our covalent bonds, when we're breaking them, when we're drawing our orbitals, all that kind of stuff comes from our valence electrons, okay? All right. So what do we talk about with covalent bonding here? So remember, at the end of chapter 7 there, right, we drew Lewis dot structures. And we said that we can use our Lewis dot structures to start to predict how many bonds a certain atom can make, right, to get to its kind of happy state, okay? Now, when we have unfilled orbital sets, right, in our valence electrons, right, there is going to be some attraction from the electrons on one atom to the nucleus on the other there, okay? That's what basically causes bonds to form, okay? Electrons see that their neighbors have a nice heated swimming pool, right? And they're going to say, I want to go make friends with them, right? And they start to make a bond with them, okay? But if we start to push these atoms too close together, okay, then the nuclei of the atoms start to interact with each other. And so we end up seeing a repulsion, okay? Now, what we're going to end up doing is showing a static bond in between two atoms, right? We draw it on paper, and our paper is not moving, right? It's a static representation of this. In reality, all of these bonds are kind of vibrating and bending and stretching and flexing, and they're kind of hanging around a stable state, okay? You can think of every bond as kind of an accordion, okay? So they're just kind of flexing back and forth, and they don't make any music for us, right? But that's important that things bend and stretch and twist and turn. But you guys already knew that, right? Because what did we learn way back in chapter 1? Well, we learned about something called what? Kinetic molecular theory, right? And it says as we add energy into a system, the molecules start to move more, correct? Now, what you guys might have thought about at that point is that when we say molecules move more, that means they just physically move themselves around. As if I asked Andy to get up and just start wandering in circles around the classroom, right? He'd be moving around. But if I asked him to get up and run circles around the classroom while waving his arms like wacky inflatable arm guy there at the car dealership, right? While kicking his legs out and doing all this, right? As you start to make him do more things, that give him more energy, right? There's different motions that he can take. It's the same thing with a molecule, okay? Atoms can rotate around their bonds. Their accordion can play a little bit louder. They can stretch back and forth. Okay, they can bend, they can vibrate, they can stretch, they can move, okay? There's lots of different motions that molecules and atoms can take. And that's where energy, if you want to think about it, is stored in a molecule, right? In these bends and stretches and this kind of thing. Now, you'll learn a lot more about this when we get to organic chemistry, okay? And we actually will discover a way how you can see those different movements of an atom and a molecule. It's very, very, very important technique, and it's a very easy technique called infrared spectroscopy, okay? So for any of you guys who are interested in forensics and those kind of things, it's one of those very common techniques that they use to identify what's that mysterious white powder that we found at the crime scene type thing, right? It's one of the techniques that they use for that.
Once had a friend cut up a bunch of garlic powder on a coffee table and snort that.
See if I'm better friends.
He was trying to convince our team coach that he had gotten a hold of something.
It's garlic. Even better on the powder.
Man. Anyway, so if we take this idea of molecules bending and stretching and playing the accordion and kind of graph things out, right? So we have one nucleus over here, we have another nucleus over here, right? If we follow the blue line here, that's as we start to bring our two atoms closer together, okay? There's some kind of ground state here, right? The happy distance at which these two atoms can live with each other. They're not too close, they're not too far apart, the porridge is just right, okay? So they're just at the right distance to make the most stable bond, but you can see that, you know, as we add a little bit of energy into this, right, these things can start to stretch apart a little bit, but then they'll want to come back together, right? We add a little bit more energy, they can stretch apart a little bit further, right? Stretch apart, right? So that's all that we're showing here, okay? There's some kind of happy ground state for that bond. And so when we report bond distance to you guys, okay, we're kind of looking at that bottom part there of that of the valley here, right? There's a happy kind of bond distance for each set of things that we can bond together, okay? That doesn't mean that it's static at that distance, okay? But that's kind of the happy medium for those things, okay? Cool. All right, so how do we start to represent this? Well, Lewis, who kind of came up with this methodology here, basically what they said is if we take two Lewis dot structures, okay, to make one bond, I need to share two electrons in between it, okay? Every bond that we draw has two electrons that are represented in that line that we draw with it, okay? So every line, every individual line that you guys draw represents two electrons. And that's why we often refer to them as bonding pairs, okay? We're going to be dealing with pairs of electrons as we go through this. We're going to have bonding pairs and we're going to have lone pairs, okay? Bonding pairs are things that are in bonds, two electrons. So let's think here for just a second. Does it make sense that I can only ever have two electrons in a bond? Well, let's see here. To make a bond, I have to mix my atomic orbitals, right? That's what I taught you guys in the first slide there, okay? How many electrons can fit in any single atomic orbital? How many electrons can fit in any single atomic orbital? Two. So now if I take an atomic orbital and an atomic orbital and I mix them together to make a new thing called a molecular orbital, what do we have? Well, we still have an orbital. How many electrons can fit in any orbital? 2. You guys got it? Okay, that's how this is going to work. Any single line that we draw represents 2 electrons in a bonding orbital. Okay? Now we're going to learn things that are double bonds and triple bonds that consequently involve 2 lines or 3 lines being drawn. Okay? But every line that you draw represents 2 electrons. So if you draw 3 lines in between things to represent a triple bond, 6 electrons there. Got it? And we'll talk about where those electrons live and why they are different. What's up?
So if you have 2 orbitals from 2 different atoms,
Yeah.
you should have 2 bonds because
No. It takes 2 orbitals to make 1 bond.
isn't there 2 electrons in 1 orbital?
There could be 2 electrons in 1 orbital, right? But that's the thing here, right? So if we have a filled orbital already,
Yep.
then why would it want to bond to something else if it has filled orbitals there already too, right? So there has to be a vacancy in the 2 apartments, right? And then they can share. All right. Here it is. Okay. So just to kind of put a point on this, right? The red and the blue here, right? The red and the blue electrons, one of those electrons comes from each of the hydrogens, right? We know that hydrogen has 1 valence electron, right?
Yes,
Yes.
How do we know what a valence electron is?
not 4.
That's fine, but give me a better definition.
It's in
It's
the outer.
on the outside of the
They're the electrons that are in the outer filled shells, right?
No.
No,
They're the outer not filled shell.
the outer partially filled shells, right? Are s electrons always going to be considered valence?
Just about.
Yeah, right? Is it important to be able to recognize valence electrons?
Yes.
Yes. Should you guys be expected to give me the electron configuration for the valence electrons?
Possibly.
Yes. Now, why would that be important? Well, we'll talk about it in just a little bit, okay? But if I am an electron living in a p orbital, okay? If I'm a valence electron living in a p orbital, do I have a different shape than an electron living in an s orbital?
Yeah.
Yes. Do you think I'm going to behave differently when I bond? Possibly. Do you think it's important to recognize that?
Yes.
Absolutely. Okay? So it's important to be able to recognize and do our electron configuration. Okay? But anyway, so we share 1 electron from each of the hydrogens, and we just represent it as a straight line in between the 2 of them there. Okay? So as a big shocker, we use a line to represent a bond. You guys have probably seen this a million times at this point also, right? So not too big of a difference there. What we're going to do is use something called the octet rule, and I really don't like that term. The octet rule is just really not a rule in steadfast. It really exclusively applies to carbon, nitrogen, oxygen, and fluorine. Okay? There's really only 4 atoms on the periodic table that exclusively follow the octet rule, meaning that we will only ever really see 8 electrons with it. Okay? Everything else can deviate from it. But that doesn't mean that it's not important, because we usually start with the octet rule. Okay? So it's really a guideline for us, right? It's, hey, let's start here and see if there's any deviations that could reasonably occur. Okay? So I'm going to always say, hey guys, don't forget to check your octet rule. Right? Just to keep things simple. Otherwise I have to say, hey guys, don't forget to start with your octet rule and then check to see if the guidelines are being followed and if there's any deviations that should occur. Right? Far too many calories to do all that. I don't have time for that, right? So when I'm saying the octet rule, that's where we start. Okay? The rule part is maybe a misnomer in some degrees. Okay? All right. So what does this say? They want to have everything wants to make bonds to get to 8 valence electrons. That should make sense, right? Ooh.
Yes.
What on the periodic table always has 8 valence electrons? What family?
Noble gases.
Your noble gases, right? So the other way you might see this described is that this is not the octet rule, but the noble gas configuration or the noble gas rule, any of these types of things, right? Why 8? Why not 12, right? Is 8 more marketable? Heck, let's do 10, right? We live in a world where the decimal system, right? We work on everything on the decimal system. 10 seems more marketable. There's 10 commandments after all, right? So why not 10?
Not cool enough.
2 in every orbital.
Huh?
2 in every orbital, 1 on each side.
What do you mean?
2 electrons in every orbital, 1 on each side. and
One on
it's-
each side, what do you mean? We're in 3-dimensional space. You have infinite sides, right?
Yeah, you do.
Yeah, you do.
It means that you basically have a lot of balance.
Well, okay, so if you have 2 per orbital, right, you have multiple orbitals.
Mhm.
So as you keep going, like, more orbitals out, don't you need more electrons to fill it? And like 8 is just basically where we're at with most of them. Oh, well, no, isn't 8 what the, this block is? The P block, right?
Maybe it would be more in terms of, like, basically the 8 electrons means that the outermost S shell is basically filled. So it's very stable.
Pick a noble gas aside from helium.
Xenon.
Okay.
What's the coolest?
How many valence electrons does xenon have? Okay. Where are those 8 electrons living?
The S shell.
2 in my S, and then what? 6 in my P. Huh. Okay. So let's pick krypton then. Okay. How many valence electrons does that have? 8. Where are my 8 electrons living?
Same. place.
2 in my S and 6. You guys get what I'm trying to get at with this? Why 8?
Oh, cause it's P plus S.
Because that's the maximum number of electrons we can fit into our S and our P orbitals. You guys got it?
Yes.
Right? If I have access to D orbitals, then we can obviously violate the octet rule here, right?
Yeah.
But the reason why we get to this magic number 8 is because we're dealing with our S and our P orbitals. Okay? How many, hang on just a second please. How many S orbitals do we have per period? Go ahead. 1. How many P orbitals do I have per period? 3. So how many total orbitals do I have?
4,
4. How many electrons can fit in an orbital?
2.
What's 4 times 2?
8.
8. You guys get what I'm saying with this, right? This is important to recognize. Extremely important, right? Otherwise, you guys, it's, oh, well, we just have disconnected ideas here. I guess 8. Yeah, sounds good to me. 8. Right? It all comes, there has to be an explanation for this. There has to be a logic behind this. Why? Because this is a science. Science is all based off of what?
Explanation.
How I feel about things. I like 8. Okay? No, there has to be a logic behind it, right? There has to be a logic behind these things. Do I expect you guys to start to see that logic?
Yes.
Yes. Otherwise, what happens? You guys start to memorize things. And in 3 weeks, you guys won't remember what you memorized, okay? But in 3 years, you will remember what you understand, okay? And that's the difference. I want you guys to understand things. I don't want you guys to memorize things. Got it? So 8 has a rhyme and a reason behind it, okay? There is a purpose to it. It comes from how many orbitals we have in our valence shell, and that's going to dictate how many bonds we can typically make. If I have 4 orbitals and I S in my 3 P's, I typically should expect to see 4 bonds. Not for everything, but if I see anything more than 4 bonds, we better go, right? Something unusual is going on here, okay? And so we will see some of these exceptions, and we'll go through some examples with all of this. But the 8 rule just kind of tells us where we should begin. It's a good place to start, okay? All right, so I already talked about the top definition there, right? Bonding pairs, or a bonding pair is just dealing with how many electrons in any single line that we draw, right? Electrons shared between atoms. A lone pair is a pair of electrons that's not in a bond, okay? So electrons that are not in a bond. So if we go into this mysterious molecule here, which we've never talked about, right? We see that we have a bond in between the oxygen and the hydrogens, okay? This is a bonding pair, this is a bonding pair, this is a lone pair, and that's a lone pair. Got it? how many electrons does oxygen have access to with sharing? Well, these electrons are living on the oxygen, okay? These electrons are living on the oxygen. So 1, 2, 3, 4. It's sharing these here, right, and it's sharing those here. So how many electrons does the oxygen have access to?
8.
8, right? 2, 4, 6, 8. Got it? This is going to be important because I'm going to confuse you guys in just a little bit because we're going to learn a new type of charge. Hang on just a second, Gabe. Okay? We're going to learn a new type of charge called a formal charge. Okay? A formal charge is different from our ionic charge. Okay? And it's different from our oxidation states. Sometimes. Okay? But our formal charge is going to be one of the key concepts that come out of this chapter. Okay? Because your immediate question should be, how do I know that it looks like that? Dr. H looks kind of shady. I don't trust him. I've never seen his degree. How do we know that he actually has a PhD in anything? Good question, right? There's got to be a logic behind all this. I don't know. You guys don't know, right? They found me wandering down Royal Well Road, and I had a nice shirt on. They said, "What do you know about chemistry?" I said, "Okay." Well, they don't know either. Come teach them something, right? Right? But there's got to be a logic behind why everything looks the way it does, and that's going to be important in our formal charges. Okay? Gabe, what's up?
Okay, you said that the noble gases have 8 valence electrons. I
Mhm.
thought the full shell had 8
Yeah.
valence electrons. So why
Right.
do you consider them p valence?
Hmm?
Why is p considered valence?
They're not. I was making a point with this, right? Just why do we say 8 for the noble gases? They don't have any valence electrons. So then we could use that to explain why they don't react as much. Well, they have filled sets, they're never defined as valence, right? And then they'll be less likely to form bonds, is what it is, right?
Okay.
I was just making a point to get to why we have 8 there, right? But it's a good observation, very good observation. Okay, so we got the idea here between bonding pairs and lone pairs, right? Cool. What did I want to do with you guys here? Well, I think this is where examples come in, right?
Yeah.
Oh, yeah. Okay. All right. So let's start out with something a little bit simple, right? Fluorine, F2. If we want to start to build a Lewis structure for this, okay? One way that we could start this is we find how many valence electrons fluorine has. Okay? How many valence electrons does fluorine have? How could we figure that out?
We figured that the S shell, or not the S shell, it's in P group. So it's going to be a outermost shell.
So 2s2 and 2p5, right, with helium there, right? So we can look at our electron configuration. We know that our valence electrons are the things that are not part of our core, the things in the outermost shell. We know that it has to have 7 valence electrons. What's up?
Could you just use your periodic
Yep.
table and look at the group?
Yep.
The last number.
Yep. Alright, so as Mike was saying there, if we go to our periodic table, let me clean this up. So many colors.
Oh.
So what I do on my periodic table is I number 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now we number 1 through 8 across the top, and I number 1 through 7 across the left-hand side there, right? The numbers across the top there tell you how many valence electrons you have, okay? So anything in our group 17, our halogens, is going to have 7 valence electrons, which would make sense, right? We have our 2 s orbitals, our 2 s electrons, and we have our 5 p electrons there, right? So everything there is going to have 7. Why is it important to always think about how many valence electrons we have? Well, remember, okay, anytime you make a bond, you start sharing an electron, a single electron. If I start out with 7 valence electrons, how many more electrons do I want? 1. How many bonds would I have to make to get that 1 shared electron? 1. How many bonds should we typically see then to any halogen? 1. Do you guys catch me on this one? This is important. Will we see cases where we have more than 1 bond to a valence to a halogen? Yes. But no, right? But those are, a little bit different. So anytime you see more than 1 bond to a halogen, what should you do? Stop and make sure, okay, that you're not drawing a mistake, right? There's got to be a reason for what's happening, and we'll talk about how to build that up. But the first thing you do when you're building Lewis structures is see how many valence electrons you have and go, there are 7 valence electrons. I expect this to have 1 bond to it, okay? That should be your line of thought. And you have to use that voice, okay? Yeah, what's up?
Before this, what was the 2s2 2p5? What did that mean?
Those are our valence electron configuration.
Just the configuration.
That's walking through the periodic table to get to fluorine there, okay? So always stop and think is what I'm really trying to get you guys to do, okay? Right. So we have 7 valence electrons. We represent those valence electrons with our dots like we have there, okay? So what we're going to do, let me just move this down here. All right, there's one of our fluorines. There's our other fluorine. Okay? And the idea here is we take that 1 electron from there, and we take that 1 electron from here. We end up making a nice new bond where, well, let me do this here. I promise there's a rhyme and reason why I'm picking certain colors too, which will become a little bit more evident later, okay? Behold. Wow. I know.
That's art.
I can tell from your stunned silence that you guys are impressed with my ability to draw a bond in between 2 fluorine atoms.
Frame that to really normal.
Okay. Nice, simple, easy. Okay. See what you guys can come up with our good old buddy ammonia, NH3, right? So take a look at the steps that I did there. I found my valence electrons. Okay. I did this, the most important thing, which was what? Think. Okay. I drew out my Lewis dot diagrams, and then I brought those together to make bonds to fill in the pairs, right?
Wait, what are we bonding in H3 with itself?
Yeah, and I said draw the Lewis structure for NH3. Too many electrons. Good. Good. Just start to get in the habit of drawing the lines in between there to represent those. Good. Good. Be careful when we start to do something kind of a little bit oddball like this. What does nitrogen look like? So remember when you're putting together your Lewis dot structures? 1, 2, 3, 4, 5, right? So 5 valence electrons. So kind of spread them out, then bring them back together. And that also makes it a little bit easier to start to predict how many bonds we have for these, right? Well, this is already a complete pair, right? But these are not. So how many bonds do we expect to see to a nitrogen? 3. Where should we draw those bonds? Well, one here, and one here, right? So we see this, we see this, and we see this, right? Put them all together. Good. Second most important thing, we have done a thing, now we need to analyze a thing, right? How many electrons are around my nitrogen? How many does it have access to? 1, 2, 3, 4, 5, 6, 7, 8. Is that okay?
It's great.
Yes, that's at our nice, happy, right, octet rule-ish type place. Got it? Always stop to make sure you haven't added too many electrons around something. Okay? If you do come to a count that's more than 8, you may not be wrong, but you should always stop and think about and double check what you drew. Okay? What's up?
Is hydrogen happy at 2?
Yes.
This is the helium.
Mm-hmm.
Okay.
Exactly, right? Hydrogen is a somewhat of an exception. Remember, the idea is to fill your valence shell. The only orbitals that hydrogen has available to it are its s, so it's happy at having 2 electrons.
It's such a simple.
What's up?
So we're happy, why the fridge does it have a charge on it still?
Where does that have a charge?
Doesn't it have a charge?
No, you're thinking
NH3
ammonium.
positive.
Ammonium is
okay.
NH4.
What is that? Oh, got it.
Don't worry, we'll get to that too.
Yeah.
What's up?
How do you know like this? Should I just practice on it?
Yes.
Now?
Yep, there is a reason why we have a certain convention for how we draw things, right? Cool, there it is. Right, and there's a couple others, if you wanted to go through and kind of practice, you know, NF3 or HF or CH4 and that kind of stuff there too, right? But the same idea for how you start to construct those and put those together, right? How many valence electrons you have, how many you need to complete it, right? Which tells us how many bonds and that kind of stuff around there too, okay? So far, so good. Let's see here, so just a couple fill in the blank here, I guess, to kind of summarize all this stuff. Electrons that are shared by atoms are called bonds or bonding pairs. Okay. Electrons that are not shared are on a particular atom, lone pairs. Two atoms share one pair of electrons, that is a single bond comprised of 2 electrons, okay? If they share 4 electrons, then we call that a double bond, and 6 would be a triple bond, and we'll kind of start to build those in as we go through, okay? Okay. 2 atoms share 2 pairs of electrons, it's a double bond. 3 pairs is a triple bond. And we won't be talking about quadruple bonds. That really only happens in very, very rare cases with certain transition metals, so really not something we need to talk about here, right? So if you draw anything more than a triple bond, guess what happens? Okay, not gonna happen.
Wait, here, this is one.
You get the red pen. The red pen of,
Disapproval.
you know, no happy stamps, or the other way, okay? So, how do we represent double and triple bonds? Okay, I think it's kind of, hopefully it should be a little bit self-explanatory, but we just put two lines in between something. So if we have O2, right, we would draw something like this, or N2, we would draw something like that, okay? Each line represents 2 electrons. So how many electrons does this nitrogen have access to? 1, 2, 3, 4, 5, 6, 7, 8, okay? So everything still is following the octet rule, okay? But there are consequences to why double and triple bonds, or when double and triple bonds form, I should say, okay? And we'll talk about how we can start to predict those in just a little bit. All right. Okay, so how or what or when or in what manner can we describe our bonds? Well, there's going to be 2 types of bonds that we're going to really be dealing with, and that's a polar and a non-polar covalent bond. Okay? And polar and non-polar covalent bonds just work off of the idea of the atoms playing tug of war. Okay? When I bond 2 atoms together, right? Remember what we did in the last chapter was this just go through and describe the idea of periodic trends. Okay? So if an atom has a certain property associated with it in terms of its radius and its electronegativity and its ionization energy and all that kind of stuff, right? It doesn't magically lose those properties as it becomes part of a molecule. It brings those properties in with it, okay? And so it should stand to reason then that if an atom is good at attracting electrons to itself, that it should maintain that property to some degree when it's bonded to something else, okay? So what I mean is this. Remember I told you guys we talked about electron affinity as a periodic trend. Electron affinity is the ability of an atom to attract an electron to itself. The smaller the radius, the more attractive that atom is, right? Does that make sense? Let's see, small radius to attract an electron. Electron has negative charge. Small radius would mean it's closer to the nucleus. Negatives like positives, right? So if I have a high electron affinity, it would make sense then that I have a large electronegativity also. And electronegativity, and we'll talk about in just a bit, is the ability for an atom in a molecule to attract electrons to itself, okay? It's basically, electronegativity is just a kind of a qualitative measure of how much CrossFit an atom does, okay? How good are they? How strong are they at pulling electrons? Okay? So let's think here for just a second. Let's say that there's a bond that's formed in between 2 atoms, okay? And both of these are of equal strength. That means that those electrons in that bond are shared equally between those 2 atoms. That means they spend 50% of their time around one atom and 50% of the time around the other. That would be equal sharing, right? Now, I've got an older brother. When I was growing up, he was much taller than I was, okay? Not anymore, now he's like here, right? So I can, right? He can't hit me, right? But he was bigger than I was when we were younger. And we only tragically had one Nintendo. So guess who played the Nintendo more often? He did, right? Not an equal sharing. So one person, right, has access to the Nintendo a little bit more than the other one does, right? That means there's a pull of these electrons towards one side of these bonds. So think about this for a second, okay? If I am electronegative, I am pulling atoms to myself. I'm pulling electrons to myself. How am I going to feel?
Negative.
Not just negative, but partially negative, right? Because the electrons are going to be hanging around me a little bit more than they would hang around the other atom. Got it? Is it a full negative? No. If it's a full negative, it'd be a ion, right? We're not dealing with ions, we're dealing with what?
Covalent.
Covalent, okay? This is important, extremely important. Partial negative charges Now, if I am drawing electrons to myself, okay, and I am bonded to Andy up here, okay, hold your hand there for a second, right? Right, if we've got a bond here and we're sharing electrons, and I pull the electrons away from Andy, how does Andy feel? I have electrons, he's feeling
Partially
positive, right? It looks like he was kind of negative in his attitude though. No, I'm kidding, right? Do you guys catch this? The electrons have to come from somewhere. If I'm pulling them away from something else, the other thing has to be positive. Partially. Okay? Partially. That's all this is. It's a game of tug of war. If one thing pulls, the other one has a partial positive. Now, what do you guys know about negatives and positives? They
attract.
attract. Okay? What do you think about partial negatives and partial positives?
They
They
partially
somewhat
attract.
They somewhat attract, and this is going to be important because we're going to learn how molecules communicate with each other. Okay? Molecules communicate with each other through these things called electrons. I know. I was shocked to learn this too. Okay?
Incredible. And what's some of these things?
But depending on where your electrons are depends on or affects how you can communicate. Okay? If you have partial negatives, you're communicating differently than a full negative. If you're partially negative, you communicate differently than if you were neutral. Okay? Extremely important. All right. So this is an ionic bond, right? This is a covalent, right? And the polar and the nonpolar is just where the electrons are hanging out, partial negatives or partial positives. And I'll show you guys on the periodic table the general trend for electronegativity, although be careful because it's not really a periodic trend, right? Yeah.
I'm just trying to visualize that, so like, is that why water, those little hydrogens are kind of like?
That's a different reason. It's a good, that's a good observation, right? But there's a different reason why that does that. That's not dependent on electronegativity, that depends on how and where bonds are arranged in space. Okay, right? What's up?
First off, why does chlorine have like a lightning bolt feather in his cap?
It's not a feather, he killed a Pikachu. That's
It's to show that he's a super evil guy.
Okay,
Yep.
second question.
Yep.
Do all halogens tend to form, polar bonds?
In general, yes.
Okay.
But it depends on what they're bound to, right?
Okay. So typically if they bond to hydrogen, it's gonna be polar.
Oh, yeah.
What about if they bond to each other?
Then it depends on what's bound to what.
So fluorine and bromine,
What about it?
if those two bonded, what would happen?
Fluorine, we'll learn about in just a minute, right, in just a couple slides.
Okay.
So good questions, but there is going to be a way that we have to figure out what is more electronegative than something else,
Okay.
right? So good question, I know now I understand where you're going with this, so we'll get there, I promise, okay? Cool. Now that we understand everything, let me give you the most important slide, okay? So, how do we start to put together more complex Lewis structures? Okay? How do we start to put together more complex Lewis structures that aren't just F2 or N2 or O2? Okay?
We put letters in a blender?
Yeah, kind of, but there's a order that we have to do this in. Okay? These are the steps. Okay? I'm going to use, I only have 3 of these per year. Okay? I'm going to use my magic professor powers to predict the future. Okay? And this is going to come true. I'm going to be a prophet. What's going to happen is you guys are going to practice and you're going to start to skip steps. Okay? And when you skip steps, you're going to get things wrong. And when you get things wrong, red marker. Okay? Don't skip steps. Don't. Okay? But I'll make a compromise with you guys. Sounds good? You can start to skip steps when you guys get your doctorate.
Really?
Okay? So, if you have now until the end of the semester to get your doctorate, and then you can start to skip steps. Don't do it. I say this every semester. And you guys go, yeah, he's talking to somebody else. Not me. You don't know me, Dr. H. I'm perfect. Okay?
So what you're saying is you've never taught Mary Poppins?
No. But don't skip steps. Okay? All right. So step one, count the valence electrons in a molecule. Cool. How do we get our valence electrons? What piece of information do we need? What table do we need? Our periodic table. Okay, so you're going to need your periodic table. You're going to need to get a valence electron count for everything. You're going to draw a skeletal structure. Okay? I'll tell you exactly how we start to put together a skeletal structure. But in our skeletal structure, we join the atoms together to a central atom, or an atom that's in the middle. Okay? You add lone pairs to form octets. You begin with the more electronegative atoms, / you work from the outer atoms to the inner atoms. Okay? You work from the outside in.
So, in the case of H2O, would that be the hydrogens you start with?
Hydrogens are an exception.
Oh boy.
Man, not more exceptions.
Okay, so like, but if you like carbon and, well, anything really, would you start with not the carbon, and you do the carbon?
What you're asking me is, I want a single definition to account to everything. And I can't do that for you. What I can do is give you 4 steps to how to do everything.
Makes sense.
Okay? Step 4 is the most important one. That's to check what you're doing. As they say, check yourself before you
Wreck yourself.
get a Lewis structure incorrect. Okay? So I think that's how it goes. You guys are gonna, that's the step that you guys are gonna skip. Step 4. Okay? Step 4 is count how many electrons. Make sure you guys didn't add anything into there that shouldn't be there. Check to make sure you didn't over octet anything. Okay? And then step, very easily. Okay? And step 4 is make sure you check your formal charges. Now I will show you guys how to check your formal charges. You can use Dr. H's patented science circle. Okay?
Really?
Science circle replaces mathematical equation in the textbook. Either one you guys want to use, I don't care, as long as you get it right. Okay? But I have problems remembering formulas. I don't have problems remembering circles. Okay? If you still have extra electrons after you did steps 1 through 3, okay, place the extra electrons around the central atom. If you have too few electrons to complete your octets, that's when you start to make your double bonds and your triple bonds. Okay? This is basically your step to success. One last important thing, which we'll kind of pick up on next time. These are all the geometries that, or let me be careful here, with imagine a heavy asterisk. These are all the geometries that exist in the known universe. Okay? Every atom that exists falls into one of these categories here. That's it. That's good news. You know why? Because that means I can only ask you guys so many questions. And there's only so many answers to it. But if you guys get creative and you get your PhDs, you're going to start to skip steps and you're going to invent new geometries. And then what happens? They're going to be wrong. Okay? Don't do it. All right? Cool. Yeah.
That was so much fun.
Well, I've got your guys' quizzes, so if you want to pick them up, just swing by.